Okay, so last time we were talking about inner product spaces. Very quick reminder. The idea of an inner product space is to sort of, hope to play off of the successes that we had creating a previous abstraction, namely vector spaces. So the big idea there was we noticed that there were lots of things, keep that ambiguous, that at least in terms of how the objects behaved is really a lot like Rn. So we made this definition of an abstraction called a vector space. Be completely ambiguous about what the objects are, but as long as things behave like things behave in Rn, then we have a vector space. So last time we did the analogous thing. We said, okay, well, in addition to vector addition and scalar vector multiplication, let's also talk about things that are similar to Rn, furthermore considering the dot product. So we're looking for things that behave like vector addition, scalar vector multiplication, and things that behave like the dot product. We defined this new thing called an inner product space, and we haven't seen applications yet, but I claim that there are going to be some big applications of inner product spaces. Okay, so the idea we're going to talk about today is orthogonality. Things that you can do with orthogonality. So a quick reminder, what does it mean for two vectors to be orthogonal? Well, in Math 212, orthogonal just means the dot product is equal to 0. Right? So it means something very close in Math 212, something very close to perpendicular. Not quite the same. Not quite the same. So perpendicular means you have two vectors that actually have well-defined directions and therefore aren't 0. And that you can say something about their directions and, 90 degrees and all. So the word perpendicular, in fact, excludes the 0 vector. It's just kind of an awkwardness of the language. Orthogonal just means the dot product is equal to 0, therefore does not exclude the 0 vector. Okay, so same story. Keep in mind in inner product spaces, the role previously played by the dot product is now just played by a new operation called an inner product. So we're going to say that two vectors in an inner product space are orthogonal if their inner product is equal to 0. Okay, so first definition, this is something that is extremely guessable. Orthogonal basis. Big surprise, it's a basis in which the vectors are pairwise orthogonal. It's exactly what you would guess. Okay. The next definition, not quite as guessable, but it's still pretty straightforward. What we call an orthonormal basis. An orthonormal basis is a basis, just like you would suspect. This ortho here suggests that the vectors have to be orthogonal. And the one other detail, and this is the refinement, the suffix here, normal. What does the normal mean? The normal means that the vectors have to be what we sometimes call normalized. Now, a quick cultural note. This word normal means lots of different things in different circumstances. Awkwardly, back in Math 212, they talked about normal vectors, and normal was a stand-in in that case for perpendicular. So awkwardly here, normal does not mean perpendicular. The ortho kind of means perpendicular here. The normality here refers to this other thing of the vectors having magnitude equal to 1. Okay, so anyway. By the way, sometimes we'll talk about vectors as being normalized if they've been scaled appropriately so that their magnitude is 1. Okay. Alrighty. So, a quick picture. Here's what an orthonormal basis looks like. We have a basis. So I'm drawing a picture of an orthonormal basis in R3. And the ortho is the fact that they are orthogonal and therefore pairwise perpendicular. The normality is the fact that their magnitudes are all 1. Okay. All right. A quick example. Standard basis, of course. That's a freebie. Go ahead and confirm that for yourselves. Easy to check. The standard basis is orthonormal. Here's a non-obvious example. this right here is an orthonormal basis for R3. Now, you got to check that these are orthogonal. Take their dot product. It's clearly 0. Got to check that these are orthogonal. Got to check that these are orthogonal. It's 3 easy dot products. They're all 0, as it turns out. Okay. Next, we've got to check and make sure they're normalized. We've got to make sure that that has magnitude 1. Likewise that, and likewise that. Again, just some arithmetic. Okay, now why do we care about orthonormal bases? What do they do for us? There are 2 big features that we're going to talk about for orthonormal bases. The first comes from this theorem right here. It's going to take me a few minutes to talk my way through this theorem, and then we'll give a kind of a geometric context, and then we'll prove it. So here's what the theorem says. We start off with a basis, and specifically you'll notice this is an orthonormal basis. Orthogonal is not good enough. It's got to be orthonormal. Okay. Given this orthonormal basis, given a vector v in your inner product space. Oh, whoops, wrong color. I wanted this to be green. Given a vector v in your inner product space. Here are 2 things that you can compute that are interesting, seemingly different, but as it turns out equal in this case. So you can, first of all, you can compute something called the coordinates. Now, I know y'all remember what coordinates are. We spent a bunch of time in section 5.3 talking about coordinates and coordinates with respect to bases, change of bases, all that business. And you'll recall then that when we talk about the coordinates of a vector, what we're talking about ultimately is how do you write that as a linear combination. So coordinates are defined based off of linear combinations. Okay. All right, now here's another thing that you can compute. Sort of a parallel calculation, I guess you might say. Something called projections. These are what I'm going to call the projections of that vector into these basis vectors. Reminder about projections. In Math 212, sometimes this is called a component. But by projection, what we mean is to what extent is a given vector pointing in the direction of another vector? And it's computed by dot products in Math 212. Specifically, if you're looking for how much does a vector point in the direction of a unit vector, it is in fact equal to that dot product. Okay, so hopefully you remember these. Again, terminology is not critical here. So what I'd like to point out, the given a vector v, these are completely different calculations. What we have in yellow here, the coordinates, we're talking about a statement involving linear combinations. When we talk about projections, we're talking about dropping perpendiculars one at a time to the individual basis vectors. So this is a calculation that's based off of perpendiculars. This is a calculation that's based off of linear combinations. They at a glance do not appear to be related, really. In fact, let me show you a picture on the next page. Given a vector, how do you find the coordinates? Well, again, a bunch of details, but roughly speaking, we're trying to write v as a linear combination. And remember, linear combinations involve, details aside, drawing parallelograms. Right? The way you scale and add vectors involves the creation of a little parallelogram. So this yellow parallelogram represents how you would compute the coordinates. Right? On the other hand, how do you find a projection or a component? Well, you drop a perpendicular in the direction of the one vector, and then you drop a perpendicular in the direction of the other vector. Right. So, roughly speaking, again, details aside, you look at that yellow picture, you look at that orange picture, these do not appear to be the same certainly not the same calculation. They don't even look like they are related, and it's not clear why they should be related. Okay. All right. Now, back over to here. What does this theorem say? This theorem says if you're talking about an orthonormal basis, then these are always the same. The coordinates and the projections are always equal, despite what's kind of vaguely suggested by this picture. All right. Now, let me give you reasonably good intuition as to why that is. Here's what it would look like if we actually did have an orthonormal basis. Notice, importantly, this vector here. The parallelogram that you would draw to try to understand the coordinates is a rectangle now. Right? And then when you drop perpendiculars, you can see how you are kind of doing closely related calculations. Right? The yellow parallelogram and the orange perpendiculars line up. Okay. Now, this is not intended to prove anything. Don't worry about the details in this picture. This is intending to show plausibly how orthonormality might make seemingly unrelated things actually turn out to be related after all. Okay. All right, so here's how we're going to go through and prove this result. The algebra makes very short work of this, as it turns out. Keep in mind we're talking about a vector v. A vector v can be written as a linear combination of the basis vectors. Let's just plug that in. Don't forget, coordinates are the coefficients there in that linear combination. So there's the coordinates right there in yellow. Okay. All right. Now, we're going to be interested in computing these projections. The idea is to show that when you compute projections, well, you get coordinates. So here we go. Let's compute those projections. Here they are. The projections are, I'll do those in orange again, just follow my pattern. Those projections. Inner product with the coordinate, with the basis vectors. Projections. Okay, well, now, don't forget, this function that says inner product with this fixed vector vi, that function is a linear transformation. The way we said this last time was that inner products are linear in each entry. In other words, if you fix the right vector, for example, view the inner product as a function of just what do you put in the left slot, right? That function that takes this vector input is a linear transformation, so linear combination in, linear combination out, like so, in the usual way. And then we have here these projections, like that. Okay, so that's just using known algebraic properties of the inner product. How are we doing so far? Is everybody on board? Okay. All right, so we're assuming we know the coordinates, we're trying to compute the projections, and we've got it down to this. Now, do keep in mind we know a couple things about our basis. We know that we have an orthonormal basis. There's a couple of things about an orthonormal basis. On the one hand, an orthonormal basis is orthogonal. Orthogonality means that these vectors are all orthogonal to each other. It means that these vectors' inner products with each other are all 0. So those inner products disappear. That's fantastic. Love it when you get zeros. Terms go away. Don't have to deal with those. But now there's more than that. Not only do I know that an orthonormal basis consists of pairwise orthogonal vectors, I furthermore know that this is a normalized basis. All of the vectors have magnitude equal to 1, so the self-inner product of vi with itself is 1. Well, it's 1 squared, right? But that's 1. So fantastic things have happened here. We get this great big expression. A lot of these terms go away because they have a factor of 0. This factor goes away because as a factor is 1. And notice all you're left with is this single coordinate ci there. It's the only thing that doesn't disappear in that in the dust of that calculation. So punchline, we are done. Keep in mind our goal was to show that given an orthonormal basis, our goal was to show that coordinates were equal to projections. We have now shown that this projection is equal to that coordinate as required. And we're done. Everybody see how that works? Nice little result. Okay. All right, so let me give you a couple of motivations. Why should we care about this? What is this good for? One is, you can see straight from this example, sometimes it's just convenient. For example, consider this vector right here, and let's consider this basis from the previous page. How would I find its coordinates? How would I find how to write that green vector as a linear combination of those given purple vectors? The theorem that we just got through proving says that coordinates are projections. So I don't have to compute the coordinates directly. Now, before we do that, let's just think through what would our alternative be if I wanted to take sort of a chapter 1 approach to this problem. I've got one vector, I've got a list of 3 other vectors, I want to write that as a linear combination of these. You write that out, it turns into a matrix equation, and you just row reduce. So you can do that, you can row reduce, but look at the numbers, fractions, square roots. Right, it's going to be an annoying calculation to go through and do that. Not that you can't do it, but certainly it's sort of undesirable. Okay. So instead, we're going to capitalize on this theorem. If you want to compute the coordinates, you don't have to do that directly. You can just compute the projections instead, and they're the same. So here we are. We compute the projections. Projections are computed with dot products, thus giving us the coordinates, and easy calculation to compute those projections. Nothing to it. How are we doing? Is everybody on board? Okay. Now, you might say, okay, well, yeah, but look, this wouldn't have been that bad. I mean, it'd be a little annoying to deal with the numbers, but in real life, I'm going to have a computer to do these calculations for me. So who cares if the arithmetic gets a little weird? That's not my problem. That's the computer's problem. Right? And sure, I get that. Here are some other circumstances that you might face. Let me remind you of calculations that you've dealt with in the past. Let's talk about linear independence. The first kind of linear independence we came up with, a question that we dealt with was, here's a list of Euclidean vectors. Is this list of Euclidean vectors independent? We realized quickly that it comes down to you make a certain matrix, you row reduce. It's no big, straightforward, right? Then we encountered some harder problems. A little bit harder if you're looking at polynomials, but still with polynomials, very quickly you can turn the question into a matrix, right? Where it got really weird was, same question, independence. Can I write these in a linear combination of those? Got really weird when we started looking at sort of random functions, just regular old weird functions with no assumptions of what they are. How do you turn that into a matrix question? It's not clear at all how you would turn that into a matrix question. And we were stumped. We could not answer independence questions by those same techniques. And we got lucky, clever observation. Wronski addresses it in certain cases in certain ways, and there's a whole story of that we're not going to rehash. But a much harder problem when you're looking at linear combinations of functions as opposed to Euclidean vectors. Okay. So you can imagine the same kind of thing here. Here we have a question about Euclidean vectors, and yeah, it's not that bad, row reduction, I suppose. But now suppose that instead of a Euclidean vector that you wanted to write in coordinates in terms of other Euclidean vectors, suppose it was some function that you wanted to write as a linear combination of other functions. There's no matrix that just naturally presents itself that you could just row reduce and sort of read the answers off of there. Right? That would be a hard problem. So finding these coordinates, if you're talking about functions, this is tough. That's hard. Right, but these projections, if you're in an inner product space, you have an inner product given, these projections are just, well, compute the inner product. That's easy. And this presents itself very nicely. Everybody on board? There's a lot of potential for this to be valuable. I'm going to point out a couple of examples of exactly this. we can't go into the details. We don't have the time in the course. But this theorem and this idea that we just talked about thinking of an orthonormal basis in an inner product space of functions is how you motivate Fourier series. That's what Fourier series are, really. The best way to think about Fourier series is in terms of how you can write one function as a linear combination of other functions and that you can compute those coordinates with the L2 inner product, namely some integrals. And you may kind of be able to sort of see this coming. And you look at Fourier series, those of you who had Math 112L or Math 122L here at Duke may recall that the way you find those, what they called Fourier coefficients at that time, was you compute certain integrals. Those are those inner products. So kind of a big deal. So roughly speaking, this theorem is at the foundation, or is a point of view of a foundation of a point of view on where Fourier series come from. Very neat, very powerful. Okay. All right. Another example. Now I mentioned Friday, I guess it was, when we first started talking about inner products, that another powerful application of inner products. Lots of details between where we are now and how you get to where I claim you can get. But image compression, right? This is a huge, huge topic. And of course, a tremendous amount to say. I'm not saying it's all linear algebra, but it's a lot of linear algebra. Linear algebra is one of the big tools there. And some of the basic ideas, sorry for the unfortunate pun, some of the foundational ideas of image compression are straight out of this theorem. It's just like Fourier series. We try to find a way of drawing images as linear combinations of simpler images. And we find the coordinates of how to write those images involved with each other by computing certain inner products. And finding, the appropriate inner product and the appropriate basis is one of the big tricks. And so lots of big ideas in there. Ultimately, it's this theorem. So this is the next step. The creation of an inner product is the first step. Using this theorem is the next step heading toward these powerful techniques. So pretty neato. Okay. All right, here's the next thing that's important to know about orthonormal bases. I'm going to make a definition here. Suppose you have a matrix whose columns form an orthonormal basis. Columns are an orthonormal basis. We call this an orthogonal matrix. That's the term. You can kind of see how this would be a plausible idea. We've seen so many situations where knowing what the columns are says a lot about what you're doing with the matrix, right? Very often you get a list of vectors that very often just turns out that you're interested in the matrix whose columns are those vectors, right? That's just very often. So if those columns have a certain characteristic, namely they form an orthonormal basis, this characteristic of the column vectors would seem like a reasonable label to put on the matrix itself. So that's my motivation for this terminology. Now, you may be wondering, why didn't I call this an orthonormal matrix? Right? Wouldn't that have seemed like a more natural choice? Orthonormal matrix? Historically, it just isn't. Historically, it got called an orthogonal matrix, and it's stuck, and that's the terminology, and it's seemingly a little bit inconsistent, and it's not going anywhere. This is how it is, weird though I think it is. I've brought this up with colleagues in the past and said, weird, shouldn't we call this an orthonormal matrix? And what would we do if at some point, we wanted to refer to a matrix whose columns were in fact just orthogonal? What would we call that matrix? can't call it an orthogonal matrix. That's already been used. That's being used by this other term, by this other concept here. So we wouldn't have anywhere to go. And I've brought this up, and the response I get is always, yeah, that's just not a thing. We don't need that. It's never going to come up. Don't worry about it. So, okay, well, that's comforting, but I think it still remains, and I'm still just a little bit, frustrated, slightly miffed. I still think we should call this an orthonormal matrix. But we're not. It's not going to happen. This is not the terminology. So, heads up, just be aware, your responsibility regarding this point going forward is that when you see the word orthogonal matrix, you've got to remember that it's not just that the columns are orthogonal. It is furthermore, the columns are an orthonormal basis, despite the absence of the normality in the term. Okay. All right. Okay. Neat result. Really surprising result. If you have an orthogonal matrix, namely the columns are an orthonormal basis, right? Stunningly, A transpose A is always the identity. And let me say that a little bit differently. Keep in mind that the thing that you multiply by a matrix to get the identity is the inverse. Another way to say this is that an orthogonal matrix, its inverse is simply its transpose. And wow, gosh, that's a shocking result. Let me explain why this is shocking. Think back to chapter 1. How do we invert a matrix? We have a scheme, right? Here's how you do it. You take your matrix, right? You put it here. You put the identity matrix next to it, and then you row reduce the whole thing. Original matrix here, identity here. When you're done, if the reduced echelon form down here is the identity matrix, then whatever that identity matrix over here turned into, that's the inverse matrix. And this is true because of fancy arguments about elementary matrices. Okay. So that's a whole sort of a scheme. If you want to invert a matrix, you write it down, you put the identity, you go through this whole mystical process, very opaque process. There's your result that just pops out. On the other hand, what we're saying here is, your matrix is orthogonal? Oh, okay, cool. That's how you invert it. Just this. Just flip it over. Flip it over the diagonal. Way easier. How could it be that easy? How could this work? Surprisingly simple to prove this result. Let's compute this product. I need for this product to turn out to be the identity. We're just going to multiply that out. And again, that's why I assert what's going to happen here is that this is going to be the identity matrix. I'm going to show that this is the identity matrix by computing its elements, sort of in some sense one at a time. First, let's think about the diagonal entries. How would I compute those diagonal entries? Well, I would take a row of the left matrix and then dot with the corresponding column of the right matrix. Keeping in mind that this is an orthogonal matrix, I know the columns of the right matrix are an orthonormal basis. The rows of the left matrix are the same orthonormal basis because it's just a transpose. So what I've got there is basis vector dot itself. And if you're on the diagonal, you're looking at the same basis vector, what you're going to get is magnitude squared. This is an orthonormal basis. The magnitudes are 1, so you get 1. And so this product matrix here has 1s on the diagonal. Yeah, everybody on board? Okay. Now let's look at the off-diagonal elements. How would you compute off-diagonal elements? You get, let's say, either up here or down here. Well, you're going to be dotting some row with, some other column. Off the diagonal in the product means that the row number and the column number are different. So the first basis vector and the second basis vector that I'm going to be dotting are different basis vectors. So this dot product in an orthogonal, it's orthonormal, but because of the orthogonality, two different vectors, the dot product is going to be 0. And so we get all zeros off of the diagonal. And there you go. There's our product. The product of A transpose times A. We just computed all the entries one at a time, and all the entries are exactly, precisely those of the identity matrix, as it turns out. It's kind of a weird calculation, weird result. So be it. How are we doing? Any questions about that calculation? Everybody happy? Okay. All right. All right, now I do have to talk a little bit about terminology. Just a quick reminder, here's the definition that I'm making of orthogonal matrix. And then we proved this theorem here seconds ago. Recall, there is a notion of equivalent definitions, right? I think the easiest sort of first example that everybody sees is the definition of E. There's like, I don't know, 6 or 7 different definitions of E that are in fact all equivalent. You assume any one of those and you can prove all the others as theorems. Or you can make a different one the definition and from that prove all the other ones as equivalent. So which one you make the definition, it's kind of a sort of a personal choice in the context, but ultimately kind of doesn't matter. You do have to pick one to be the definition, but it doesn't matter which one. That's the situation that we're in here. The book chooses to make this the definition of an orthogonal matrix. I'm a little uncomfortable making this a definition. I feel like definition should be, I don't know, this is just an aesthetic point, but I feel like definitions should be motivatable, right? What would be my motivation for choosing the word orthogonal to describe a matrix whose transpose is its inverse? I don't know. I can think of all sorts of words that would seem to be more naturally associated to this little algebra right here. Yeah. On the other hand, I think this one makes a lot of sense. Orthonormality is the key idea in this definition that what I'm calling the definition, and that motivates the choice of the word orthogonal. I refer you to my earlier discussions about orthonormal versus orthogonal. But anyway, I think this makes more sense as a definition. It's more natural, sort of determinologically more natural. So the book and I do make different choices here for the purpose of Math 216 exams, midterms and the final. This is the definition of orthogonal matrix. Okay. All right. Okay. Why do we care about orthogonal matrices? It's because of this fact down here. If you have an orthogonal matrix, that matrix preserves dot products. Let me tell you what that means. This is what it means to preserve dot products. Here's that matrix A. By preserve dot products, what we mean is if you have a couple of vectors, and if you dot them, here you go, v dot w, right? That dot product of these vectors will be exactly the same as what you would have gotten if you had first multiplied both of those vectors by A and then dotted them. So the action of multiplying vectors by A does not change the dot product. Thus the term preserves the dot product. Yeah, everybody on board? Just terminology? So in order to prove this result, I've got to do a calculation. I have to show that this calculation works. No big deal. There's a little algebraic identity that I'm going to have to use to prove this. Here it is. That very first step. I hadn't talked about this back in Chapter 1. I suppose we could have as long ago as Chapter 1. We just didn't have any need for this at the time, and we had enough going on as it was. So I think it makes sense to wait and make this observation when we need it. And here, of course, is how a calculation goes if you dot two vectors. You write the vectors down, and you pairwise multiply and add. That's what a dot product is. Now, let's look over here. Transpose the first vector to make a row matrix, and then this says matrix multiply this row matrix times this column vector. How would you perform this, what I like to call transposed matrix product? Well, you would take these numbers and pairwise multiply and add. It's the exact same arithmetic as you would do here. Right? So ultimately, it's not that big of a deal, this calculation. It's just observing that really that these are kind of alternative notations for the exact same calculation. Right? That ends up being convenient sometimes. This is one of those times. So my first step is simply to capitalize on this choice, that I can rewrite this dot product as a transposed matrix product, and we'll proceed from there. Okay. So next step, recall transposes of products are products of the transposes. Don't forget to change the order when you cite this result. This goes way back, chapter 1, section 4. Give it a look. Transpose of a product is the product of the transposes. Change the order. Matrix associativity. I can sort of reorient the parentheses however I'd like. Let's do this multiplication on the inside here first. Notice that I have then A transpose times A, which for an orthogonal matrix is the identity. And so that cancels, thus leaving us with only a transposed matrix product, which is a dot product, and we are done. It's a very slick and convenient little calculation. How are we doing? Everybody on board? Okay. All right. So this has some powerful consequences. The fact that it preserves dot products, orthogonal matrices preserve dot products. Quick observation: if dot products are preserved, the action of multiplying by A doesn't change any dot products, then it also isn't going to change things that are computed directly from dot products. And we talked about this last time, all of the different things that you can compute just with dot products. Magnitudes of vectors, which we interpret as distances and lengths, right? Those kinds of things computed strictly with dot products. And angles computed directly with exclusively by dot products or inner products. So if an orthogonal matrix preserves dot products, if it therefore preserves everything we can compute from dot products, what that means is multiplication by an orthogonal matrix does not change distances, it does not change angles, does not change lengths. What that means is the action of multiplication by A is what I like to call a rigid motion. So for example, if you just kind of rotate like this, that's a rigid motion. No distances are changing there. Right? Any angles you might be looking at. Let's look at this angle right there. Right? This angle kind of out of the crook of my fingers. That angle, because it's rigid, it's not changing. Right? So orthogonal matrices have a very, very simple geometric interpretation. Orthogonal matrices are rigid motions on Rn. How are we doing? Okay, real quick, there's a super fun little argument that can be made. We just don't have time to do it here in class. It's been quite a few years since I really had time for this in class, but if you're curious, it turns out there's a wonderful feature of this, the collection of all non-reflective rigid motions in R3. It's called SO3. This is a very odd little set. It has a stunning feature, very geometrically interesting. If you are curious, this is not at all Math 216 content. If you are not interested, don't worry about it. But if you are curious, come talk to me after class. It's got an amazing proof, and it's a lot of fun. It takes about 10, 15 minutes to talk about. Feel free to talk to me after class. If you're interested, again, it's not required. Okay. All right. So we've seen some useful properties of orthonormal bases. And here's a reasonable circumstance we find ourselves in. Suppose we have some basis that that falls into our lap randomly. It's a basis. Hey, bases are nice. You do cool things with bases, right? but it's just some random basis. Suppose we would like to be able to capitalize on the very cool features of an orthonormal basis. Can I take my just random basis off the street? Can I go through some process that will turn it into an orthonormal basis where I can where I can capitalize on my powerful theorems? Very reasonable thing to want to do. I mean, all else being equal, wouldn't you rather do business with more tools in your toolbox as opposed to less? So, can you orthonormalize your basis? The answer is yes. There's a process. It's called Gram-Schmidt orthonormalization. It sounds much more intimidating than it really is. This is ultimately a very simple idea. This idea, how hard it seems divided by how hard it is. One of the biggest values that I'm aware of in math. This is so much easier than it sounds like it ought to be. So here's the process. It's very straightforward, really. If you have what I'm going to call a bad basis, so it's not orthogonal, it's not normalized. There's just nothing good about this basis. Let's address it one vector at a time. Let's start with this first vector. This first vector, I wish it were of unit length, but it isn't. How can I fix that? Divide it by its own magnitude. Nothing to it. We fixed that first vector. Impressed? I hope not. What a simple idea, right? Normalizing a vector is really easy. Okay. Next question. Second vector. Now this one's a little trickier. Here's what I don't like about that second vector. That second vector, I wish it were orthogonal to that first vector. Let me say that a little bit differently. This red vector here has a piece of it that is the orthogonal thing that I want, but it also has a piece of it that is parallel to V1. Right? Wouldn't it be nice if I could identify this light blue vector here, the part of W2 that is pointing exactly in the direction of V1, if I could just identify what that blue vector is. How about this? Take the red vector, subtract this light blue vector, and that would give you this purple vector that, as desired, is orthogonal to V1. Turns out that we can totally write down a formula for this light blue vector. It's not that big of a deal. And once having identified the part of W2 that we don't like, throwing it away results in something that we do like. So there's details to discuss, but we're gonna do that. We're gonna find this purple vector there, and of course, what I don't like about that purple vector is that it's not a unit vector. Right, I would like to normalize just like I did with V1. So you take that, divide it by its own length, and bam, there is your orthonormal basis. So that's the big idea. It's not deep. Right? It's very straightforward little process. Strategically, that's what it is. Now, let's talk about details. There are some details. Okay, the first step is again, as previously discussed, this is easy. If you have a non-normalized vector and you want to normalize it, well, divide by its own magnitude. Math 212, ancient history. Right? Any questions about that? Everybody remember this from like the third day of Math 212? Okay. All right. Okay, next question. A little trickier. Given that we have the first vector figured out, I would like to understand that light blue vector as we discussed. I would like to figure out the part of W2 that's pointing in the V1 direction. Once I identify that light blue vector, that is going to be the thing that I'll want to subtract from my original bad W2 vector to get, reminder, to get my new and improved second vector, that purple vector there. Right. So it all comes down, I know I'm going to subtract it off, right? It all comes down at this point, can I compute what this light blue vector is? Excuse me. Can I compute that light blue vector? Let me write down what I know about this light blue vector. I know a couple of obvious things about this light blue vector. On the one hand, I know that it is pointing in the V1 direction, right? That's kind of by assumption. Points in the V1 direction. Okay. The other thing that I know about this vector, this light blue vector, its magnitude, how long is it? All right, let me kind of drop a perpendicular here. Its magnitude is simply the component of W2 in the V1 direction. Or as you might say, it's the projection of W2 down to the direction that V1 is pointing. And projections into directions defined by unit vectors, those projections are computed with inner products. If this were Rn, this would be the dot product. And so there you go. There's your light blue vector. I know its magnitude. I know its direction. Multiply. Boom. There it is. So this thing here is what you subtract, and that leaves you with this dark blue vector, or I guess that's who we're calling this purple. You've got that vector with that formula, and once you have that vector, again, super easy to normalize. You just again divide that vector by its own magnitude, and there you go. So that's all of the formulas for Gram-Schmidt orthonormalization of a pair of vectors. How we doing? Okay. All right. Okay. What if you have more than two vectors? What if you have three vectors? Good news. The first two, it's the same process. You fix the first vector by just normalizing it. You fix the second vector by realizing that what you don't like about it is, to whatever extent it's pointing in the direction of the first vector. Nothing changes. Same exact formulas. So we don't have to repeat those formulas or rip-offs on the previous page. The worry is how you fix that third vector. How do we fix W3? The answer is not that different from what we did on the previous page. We just have to recognize there's not just one thing wrong with the direction this vector is pointing. There are two things wrong with the direction that vector is pointing. To some extent, that vector is pointing in the direction of V1. Formula from the previous page. That's how you figure out the extent to which that vector is pointing in the direction of V1. Obviously, if I want to know the part that's not pointing at all in the direction of V1 or V2, I'm going to have to get rid of that. Right? And then, likewise, to some extent, that vector points in the same direction as V2. Analogous argument. How much does W3 point in the direction of vector V2? There you go. You know what direction that orange vector points. You know what its length is. Its length is that projection. Boom. And with that identified, you take that red vector, the vector that you're starting with that you don't like because it's not pointing the right direction, subtract that light blue part, subtract this orange part. You're subtracting off the parts of that red vector that you don't like. And what you are then left with is the part that you do like. Right? Notice the structure of this calculation. It's totally analogous to the two-vector case. It's just that now, in dealing with that third vector, there are two previously fixed vectors, and therefore two components that you have to remove, and therefore two terms that you subtract, corresponding to those two previously fixed vectors. So you can probably guess what would happen. Let's imagine, I can't draw the pictures, right? But suppose you had a basis consisting of four vectors. That means we're in a four-dimensional space, right? Creepy. You can't visualize it, right? But you can still fix that first vector by normalizing. You can fix the second vector by realizing kind of deal with the part that's in the direction of the first vector. You can fix the third vector by removing the parts in the direction of the two previous vectors. You're going to fix that fourth vector by removing, with 3 subtractions, the parts in the direction of the 3 previously fixed vectors. And don't forget to normalize each step along the way. So there's the process. Like I say, there's a bunch of details involved, but the big idea is really not that hard of an idea. It's always really the same picture. So the most important thing, make sure you understand this formula. What is the structure of these terms that are getting subtracted at each stage along the game? And we will pick up here on Wednesday. Okay. Y'all have a good day. See you later.